Yeah, so what I'm going to do is to briefly summarize what we did last time. If you still remember, last time I started off by specifying a vector autoregression model. Then I summarized it, and then in the analysis that we did, we were using the summarized version of the autoregressive vector, autoregressive the vector autoregressive model. So let me just write the summarized version, the summarized using the variables that we used last time. We had GDP and money supply. And the model that we used was something like this. I'm adding something. The model that we used did not have a constant, but I'm going to have a constant to add a constant. And all the variables at the same maximum lag. And we can call this beta I, what, GDP, T minus I, plus the other one, running up to P, then we can call this J is equal to 1 up to P. And this we can use gamma J money supply T minus J plus the white noise error term. And for money supply, we had okay, this is GDPT, and this is MT is equal to we can call this alpha 1 and this one alpha 2, just to differentiate them, plus the summation of I is equal to 1 in sigma I GDP T minus I plus J is equal to 1. We can use this as our parameter, then M T minus J plus white noise error term. We can call it E2. This is E1T. The other one is E2T. All right, so this is the model that we started off by looking at. And I said that if you specify your model like this, it means your variables are integrated of order 0. So you can only specify this type of model when all your variables are integrated of order 0. That's what we have did last time. So it means the variables in this case, the variables are integrated of order 0. That's why we've specified our var model in this manner. We've specified we a model like this to talk about the conditions which would result in the just a moment. Okay, let's continue. So I last time we talked about the condition for unidirectional causality from money supply to GDP, right? For there to be unidirectional causality from money supply to GDP, that is money supply to GDP. Right. Trying to sort out. Okay, so for unidirectional causality from money supply to GDP, what did we say? Who can still remember the condition? For money supply to GDP, we said in the GDP equation, this summation of gamma, summation of gammas, these parameters gamma j's is not equal to 0. If there is unidirectional causality from money supply to GDP is not equal to 0, but the parameters of GDP in the second equation, the parameters of GDP in the second equation, the raw i's are equal to 0, are equal to 0. We said if this is the case, it means the parameters of GDP in the second equation are equal to 0, while the parameters of money supply in the first equation are not equal to 0, which means that money supply influences GDP in the first equation, but GDP does not influence money supply in the second equation. And we said this is the condition which would give us unidirectional causality running from money supply to GDP. And for unidirectional causality running from GDP to money supply, unidirectional causality running from GDP to money supply, we said that the conditions that must be satisfied are from GDP to money supply. It means in the first equation, the summation of the gamma j's in the first equation are equal to 0, while the parameters of, or the coefficients of GDP in the second equation, which is the raw j's in the second equation, are not equal to 0. So if the raw j's are not equal to 0, it means GDP influences money supply. And if gamma j's are equal to 0, it means money supply does not influence GDP. So this is what gives us unidirectional causality running from GDP to money supply. This is what gives us the unidirectional causality from GDP to money supply. And we also went on to talk about what in bidirectional causality, which is a situation where the two variables are both causing each other, right? The two variables are both causing each other. So bidirectional causality, let me just summarize it. Bidirectional causality, BDC. So the conditions for bidirectional causality are that the summation of the gamma j's in equation 1 is not equal to 0. And also that the summation of the rho j's rho I is not j, it's rho I. In equation 2, so this is rho I. You were supposed to correct me here. It's supposed to be rho I. Rho I is also not equal to 0 for there to be bidirectional causality. So it means in equation 1, money supply is causing GDP, and in equation 2, GDP is causing money supply. So this is the condition for bidirectional causality. And lastly, the condition for independence, where we are saying the two variables are not related to each other. So the condition for independence, these are the 4 conditions we discussed. So the condition for independence is that a summation of gamma j's is equal to 0. And also the summation of the rho i's is also equal to 0. So these are the 4 conditions of causality that we discussed. These are the 4 conditions of causality. And after discussing this, we then went on to specify the hypothesis of Granger causality. For example, if we want to test whether money supply Granger causes GDP, or to test whether GDP Granger causes money supply, we specified the hypothesis that we use in order to do those Granger causality tests. So if I make a mistake, please correct me. I don't know what the problem of this group is. Are you afraid of me or what? Because you are not free to participate. You don't say anything. You shouldn't be afraid of your lecture. Or are you afraid of yourselves? You don't want to see other people. You don't want other people to see that you also make mistakes. Everyone makes mistakes. That's why I'm telling you to correct me. We all make mistakes. So the causality hypothesis to test whether money supply Granger causes GDP, the null hypothesis is that the null hypothesis is summation of the gamma j's is equal to 0, right? And this is the null hypothesis, and the alternative hypothesis is that summation of the gamma j's is not equal to 0, where the null hypothesis is saying that money supply does not Granger cause GDP. And the alternative hypothesis says that money supply Granger causes GDP. So this is the hypothesis we use to test whether money supply Granger causes GDP in the first equation. And in the second equation, the null hypothesis for GDP Granger causing money supply is summation of rho I is equal to 0. This means GDP does not Granger cause, this is the null hypothesis, GDP does not Granger cause money supply. And the alternative hypothesis is rho I is not equal to 0, which means GDP Granger causes money supply. So this is the null hypothesis, and its alternative is the second one. And we said that if the p-values are less than 5%, if the p-values are less than 5%, we reject the null hypothesis and conclude that the variable Granger causes the other variable. Okay. So this is what we discussed. And when we were using the vector autoregression model, where variables are integrated of order 0. So this is what we discussed. Now, we also looked at a model where the variables are integrated of order 1. If you still remember, we also looked at a situation where the variables were integrated of order 1. So for the situation where the variables are integrated of order 1, what it means is the variables have to be differenced. They have to be differenced. If the variables are integrated of order 1, then we use them at the order at which they are stationary. So using the same model that we used last time, so we would have change in GDP on one side, change in GDP, change in GDP, T is equal to, I'm not going to leave out the constants, right? I will leave out the constants so that I summarize the model. So with our P, I is equal to 0, so not 0, it's 1. I is equal to 1. Then beta I change in GDP, T minus what? Minus I, plus summation of that up to P, J is equal to 1. Then let me be consistent. Gamma J, a change in M T minus J plus U1T, right? So this is the first equation in first differences. The second equation in first differences is change in MT. Change in MT is equal to summation of I is equal to 1 rho I a change in GDP T minus I, this must be I, not 1, it's supposed to be I, minus I, plus summation of that J is equal to 1. What parameter did we use? We used, okay, this sigma j change in mt minus j plus u2t, where u1t and u2t are white noise error terms. So this is the what? The vector autoregression model when the variables are integrated of order 1. And I said, for you to be able to use vector autoregression model, all your variables are supposed to be integrated of order 0, or all your variables should be integrated of order 1. So those are the only two circumstances where you use the vector autoregression model. If all your variables are integrated of order 0, or all your variables are integrated of order 1. So this is the model. And for the hypothesis as to whether money supply Granger causes GDP is the same. Summation of the gamma i's are equal to 0 for the null hypothesis. Summation of the gamma i's are not equal to 0 for the alternative hypothesis. And the null hypothesis for whether GDP Granger causes money supply, summation of rho i's are equal to 0, and summation of rho i's are not equal to 0. Those are the hypotheses. So these are the what? This is how you specify the vector error correction, vector autoregression model. And we also went a step further and said that if the variables that are used in the vector autoregression model are co-integrated, if there is a long-run economic relationship between the variables included in the vector autoregression model, you can specify the error correction, the vector error correction model. And the difference between the vector error correction model and this vector autoregression model on the screen is that the vector error correction model would add the error correction term. We would add the error correction term. For example, in the first equation, we would add an error correction term, which is given by lambda ECT. ECT lagged once, lambda ECT lagged once, plus this white noise error term. And in the second equation, so we would have lambda 1, right? In the second equation, we would have lambda 2, the ECT T minus 1 plus. So this is, if you add the error correction terms like I've done here, if you add the error correction terms to this vector autoregression model, then you have your vector error correction model, which we called the VECM, vector error correction model, right? Vector error correction model. So this is what would give you the vector error correction model. So you only specify the vector error correction model after you have tested for co-integration and found that there is co-integration amongst the variables that are included in the model. Okay.
Prof. Sunde. Prof.
Someone wanted to ask a question?
Yes, it was me who wanted to ask.
Yes.
In the second equation, where it's stipulated to say GDP Granger's money supply, in our first where I see summation of pi and summation of that's yeah there, and the other summation with the with
Yeah,
the sign that looks like an S.
this one.
So my question is, I wanted to understand, yeah, that one. I wanted to understand if those variables, those letters, are of fixed. If let's say, can they be replaced? Like me saying summation of bi and summation of yj perhaps, or are they fixed for us to be using that
No,
in
no,
our
no, you can use
second?
whatever you want.
Okay.
Instead of using this, I would have used this W as my coefficient, or I would have used the what? This is sigma is my coefficient. I would have used anything. Yes, so they are not fixed.
Oh, okay, okay, I see.
All right, it's okay.
It's okay
All
now.
right, so go on. You still wanted to say something.
No, no, I'm fine.
All right. Okay, so let's now go to the estimations because there's a whole lot to cover. So let's go to the estimations. I've given you the background of what we did last time, because this is basically almost all the things that we did last time. But then there's also something that we discussed where I said that most vector autoregression models do not have the same number of flags for all their variables. You may find that the maximum number of flags on M is different from the maximum number of flags that you are supposed to use on GTP. And I said, if that is the case, then the approach we use is different. And for that explanation, we didn't record that lecture. That is what we covered in the lecture last time, where I tried to explain what you do if the number of flags on your variables are different. This is where I said, if the number of flags on your GDP variable are different from the number of flags you are supposed to use on the money supply variable, then you don't estimate the two equations, the GDP equation and the money supply equation, together is in your views. You don't do it that way. You don't estimate them at the same time. But you would have to estimate the first equation on its own and the second equation on its own, right? These two equations that I've just removed here, you would estimate them separately, one at a time, if the number of flags on your variables are different. That is what you do. You estimate those two equations separately using ordinary least squares. So that's the explanation that I gave. Then let's now look at our model. I'm going to be using three variables to illustrate what we are going to do. Maybe since the number of observations, okay, let me use three variables. I'll use GDP, PCE, and PDI. So those are the three variables that I'm going to use. Now, to estimate a vector autoregression equation, you just right-click on the highlighted variables and open them as a var. That is vector autoregression. Open them as a var. If you open as var, this is what comes up. You have your three variables. They are given here. Then you have one model, and the number of flags is 2 on each of the variables. That is what is being allowed here, is two lags per variable. And this is the constant as we know it, and this is our sample size. Right, so we have one model, 2 lags, and we have 3 variables. So this is what this information is representing. So to estimate this var, you just click on OK. And these are the results that you get. These are the results that you get. Okay, so if you look at here, you can see this is the standard error in the middle. This is the coefficient of the variable at the first lag. The coefficient is this one. Then the number in the round brackets, this one is the standard error. These are the standard errors shown here. And the t-statistics is the one in the square brackets. So t-statistic, square brackets, standard error, round brackets, and the coefficient is the one that is not in brackets. If you go to the next variable, say at first lag, this is the coefficient, this is the standard error, and this is the t-statistic. And like I said, if the t-statistic is greater than 2, then you know that that variable is significant in explaining the dependent variable. So these variables on top are our independent variables. So the independent variable, if we take this first independent variable, GDP, and go downwards, I'm sure you can see that. You can see that this is the first lag of GDP, second lag of GDP, first lag of PCE, second lag of PCE, first lag of PDI, second lag of PDI, and the constant. So it's actually similar to the equations that I wrote earlier, right? It's similar to that because each equation is 2 lags. Because this is what I explained earlier, that in E-views, all these 3 variables, GDP, PCE, and PDI, are given the same lag length. But if you have used another method and found that the lags are different, that's when I said you would have to estimate the PCE equation on its own, the GDP equation on its own, and PDI on their own. If their lags are different, then you would have to estimate each equation separately. But in this case, we are assuming that the lags are the same because if use is given each variable a maximum lag of 2. Then if you go to the PCE equation, which is this one, it's also explained by the same variables, explained by the first lag of GDP, second lag, PCE, and this second lag, PDI, and this second lag. Same applies with PDI. It's also explained by the same variables. I'm sure you still remember, I said that GDP, in this case, if we look at this model here, GDP is being explained by PCE and PDI. Then PCE is being explained by GDP and PDI. And PDI is being explained by GDP and PCE. So that is what explains what we have here. So this first row is representing the equations, right? The GDP equation, PCE equation, and PDI equation. And these variables here are the independent variables, which explain these dependent variables. Then the other thing of interest that you need to look at is the number of observations that we have after adjustments. This one. The number of observations you have is 32, which means you have 32 data points, right? 32 data points after adjustment, after adjusting for degrees of freedom. Then you go to the bottom. The number of coefficients that you have is 21. Can you see that? The number of coefficients is 21, which means for this model that we are estimating, it is 21 parameters. It is 21 coefficients, right? It is 21 coefficients. And we can count them. We can count them. We come here. This is 1, 2, 3. 1, 2, 3. Then going down is 1, 2, 3, 4. 4, 5, 6, 7 constant. So 3 by 7 gives you 21. So that is where we are getting That is where we are getting this number of coefficients, 21. So the point that I want to make here is that, and must get this very, very clear. If the number of coefficients in your vector autoregression equation is more than the number of observations after adjusting for degrees of freedom, then you cannot estimate that equation. You cannot estimate that model. In this case, we are able to estimate this model because the number of observations after adjusting for degrees of freedom is greater than the number of coefficients in our vector autoregression model. So the number of coefficients is 21, but we have 32 observations after adjusting for the degrees of freedom. So it means we can estimate this vector autoregression equation because the number of observations, which is 32, after adjusting for degrees of freedom, is greater than the number of parameters, which is equal to 21. So if this is the case, it means we can estimate our vector autoregression model. If the number of observations is smaller than the parameters, then you cannot estimate that vector autoregression model. So vector autoregression models, because of the lags on the variables, you have too many parameters, which means when you are estimating the vector autoregression method model, you have to have a large number of data points, a large number of observations. That is what allows you to estimate the vector autoregression model. Okay? So you must have a large number of observations. So having done this, now there are a number of things that I want us to do. First, we want to estimate, we want to find the lag length, the appropriate lag length for this model. What is the appropriate lag length for this model? So to do that, we go to view, then you go to lag structure, and then you go to lag length criteria. View, lag structure, lag length criteria. Then you click OK. There is a number of lags suggested there. Don't change anything. You just click OK. And according to the FPE, the archaic information criterion shows Bayesian criteria and the Anagwini, all of them are suggesting that the appropriate lag length is 1. So that is what they are suggesting, that the appropriate lag length for this model is 1. I'm sure you can see that. Right. So this is the appropriate lag length using these VAR lag order selection criteria, right? All these. So the appropriate lag length is 1. So the next thing that I want us to do is to back to the equation. What's happening? Okay, we are back to our VAR. So we've tested the lag length. Now, instead of using the lag length that has been suggested by eViews, we are going to just maintain this lag length of 2. But in this case, it's difficult for us to see which variable is significant. Yes, we can tell this one is significant because the t statistic is greater than 2, even this one and this one. This one is not, this one is not, this one is not. This one is not. Then if you go down, All these are not significant. All these are not significant, except this one is significant. All these are not significant. This one is significant. These two other are not significant. Right, I'm sure you can see what I'm doing. But there is a way that we can use to see the probabilities. So I want us to see the probabilities associated with each of these lags, explaining the dependent variables. So let's do that. You go to proc. We want to generate probabilities. We want to generate probabilities from this vector, or come up with we get the probabilities. We want to see the probabilities associated with this model. So to do that, you go to proc, and from there you go to make system. Then you choose order by variable. If you choose order by variable, it means GDP and its lags are placed in one place. PCE and its lags are placed in one place, one after the other. Then PDI and its lags are placed one after the other. If you choose order by lag, it means you will have, in your equation, you will have what? The first lag of GDP being followed by the first lag of PCE, being followed by the first lag of PDI, which may be difficult to read. But if you choose order by variable, it means the first lag of GDP is followed by the second lag of GDP. The first lag of PCE is followed by the second lag of PCE, and so on. So it's usually advisable to choose order by variable so that the lags of the same variable follow each other. So we choose this. This is what I'm talking about. If you look at the GDP variable, the first lag of GDP is followed by the second lag of GDP. The first lag of PCE is followed by the second lag of PCE. First lag of PDI followed by the second lag of PDI. So this one is easier to interpret. Now, this is our model. This is our vector autoregression model. And you can summarize these lean GDP1, lean GDP2 by using that summation model that we've been using. You can summarize them by using that. So to estimate this equation, if we estimate this model that we are seeing here, then we will be able to see the probabilities. So I just click on estimate, and you don't change anything, you just estimate. So this is the model. Right. So as you can see, these are our models. The three equations that we were seeing, the first one is this one. This is the first equation. And the second equation is the lean PCE equation. And the third equation is the lean PDI equation. All of them are represented in these results. Now, the reason why I didn't, if you still remember, we tested for lag length. And E-views told us that the optimal lag length is 1. And I said, I'm not going to use that lag length of 1. I'm still going to maintain the lag length of 2. So these results that you are seeing are results in which each variable has a lag length of 2, not 1, the optimum. Right, now, there's a trick that I want to show you here, which you can use when you are doing your research projects. There are some variables that are insignificant here, because if you look at this first coefficient is insignificant, this one is insignificant, the third one is significant, this one is insignificant, this one is significant, insignificant, this one is significant. This one is a smaller probability, we can give it benefit of doubt. This one is insignificant, this one is significant, insignificant, insignificant. This one is closer to is small. This one is small. We can leave those ones. This one is high. This one is significant. This one is small. This one is significant. The last two are not significant. So the trick that we want to use here is we want to identify all those parameters that are insignificant. Let's write them down. Those that are insignificant, it's what? C1, C2, C1, C2 are not significant. Then you go to C4. C4 is not significant. Then you go to C5. It's also not significant. C5. Then you go to C6. C6, not significant. You go to C9. C9. Then you go to, we picked C9, then C11. C11. From C11, C12, C13. So 12 and 13 as well. C12, C13. And the C14, we can give it benefit of doubt. C16 is insignificant. From C16, we go to C20 and 21. 20 and 21. Right. So what do we need to do here? We need to eliminate those variables that are insignificant. Right. So to do that, you go to specification. You click specification. It takes you back to this equation. Then we want to eliminate this C1. We have C1 here, C2 there, and so on and so forth. So we are going to eliminate C1 and C2. C1 and C2. We eliminated those. So you just delete them. You just delete them. Then C4 and C5. C4 and C5. You just delete those, C4 and C5. Right? So this is what you remain with on that equation. Then C6. C6 is also going. It's also going. Then we go to C what? 9 and C11. C9 and C11. C9 and C11. And C12 as well. C12. Okay. Then we go to C13. C13. Where is that? To 16. C16. We remove that. Then C20 and 21. C20 and 21, the last two. Which means the model that we remain with is this one, right? This is the model that we remain with. So we just estimate this equation, this model, the new model that remains. I want you to pay attention to the results that we get here. Pay attention, look at these results. Can you see? Almost everything is significant. Can you see that?
Yes, sir.
Yes, sir.
Yes. So this is a smart way of doing your. So instead of following the lag length that if you suggest to you, you can ignore it and do like what I've done. Then you eliminate those lags, which are insignificant. So the model that you come up with, this model that we've come up with, this model result that we've come up with is referred to as this is referred to as the parsimonious model. This is the parsimonious model. Parsimonious model. You get the parsimonious model after eliminating those variables or those lags of variables which are insignificant in explaining the dependent variable. So you just remove them. In fact, before removing them, we were actually supposed to test them. We were supposed to say, see whatever, all those variables that were on the right-hand side, the one that I had written in blue, you were supposed to say C1 is equal to C2, C3, up to the last one, C21 is equal to 0 against the alternative that they are not equal to 0. We're supposed to test that redundancy test, the redundancy test that we did in the first lecture. We're supposed to use that redundancy test. And I'm sure we would have found the fact that all those lags of variables are redundant in explaining our model. So if you have results like these ones, then it's very easy to what? They are very easy to explain, and you have too many stories to talk about when discussing your results, because you come up with a parsimonious model. And you can still use this type of a model, the parsimonious model, in a RDL and even in ordinary least squares. You can apply this where you eliminate all those variables that are insignificant, the lags of variables that are insignificant, so that you remain with those that are significant. So you can use the same trick for an ordinary least squares equation and also for the RDL model. So let's look at this. So the first equation, look at the first equation. The first equation, which is this one, this is the equation that we remain with. And look at the Debye-Watson statistic. Does it suggest autocorrelation? I'm not sure. We can test that. We can test that. Then if you go to the second equation, the Debye-Watson is 1.7. This suggests there is no autocorrelation automatically. And this one is also close to 1.7. It may suggest that there is no autocorrelation. Then if you go to the last one, it's above 1.7, which means there is no autocorrelation. Because I said, for there to be no autocorrelation, the DW must lie between 1.7 and 2.3, if you still remember what we called the rule of thumb. So it's possible that there is no autocorrelation in all these models. Yes. There is no autocorrelation in all of them. So that's one thing. Then the other thing is using this, the importance of this model is for us to test whether PCE Granger causes GDP. And in the second equation, we are testing whether GDP and PCE Granger cause. Sorry, in the second equation, we are testing whether GDP Granger causes PCE, because we are not interested in PCE Granger causing itself. Then if you go to the last equation, we are interested in knowing whether GDP Granger causes PDI or PCE Granger causes PDI. And the PDI, we are not interested in PDI Granger causing itself. I'm sure you still remember. So having said that, to do the test, to do the test for the first equation, whether PCE Granger causes GDP, we are saying our null hypothesis in this case, since we only have one coefficient for PCE, our null hypothesis is that in the first equation, our null hypothesis is that C3 is equal to 0. And the alternative is that C3 is not equal to 0. In other words, we're saying PCE does not Granger cause GDP, and PCE Granger causes GDP is the alternative. So that's the first equation. So how do we do the Granger causality test? To do the Granger causality test, you go to View, then you go to Coefficients Diagnostics, you go to World Coefficients Test. Then you just type in the what? The null hypothesis, C3, C3 is equal to 0. C3 is equal to 0. And then that. I'm sure you can see C3 is equal to the probability value is equal to, and the chi-square is very high. The probability value is that. What is our conclusion? What is our conclusion? Those of you who were present in the previous class and even today, I mentioned that. What is the conclusion? We only use this part of the results, only this part.
We reject the null hypothesis.
Yes, so PCE Granger causes GDP, right? So PCE Granger causes GDP, right? So if you want to go back to the model, we just go back. This is the model we are estimating. We estimate it again to get the results. These are the results. So if you want to know whether a variable Granger causes another variable, you just look at whether it is significantly explaining the other variable. So in all these tests that we are going to do, you can see that all the variables that are here are significant in explaining the independent variables. So if we do the Granger causality test, we actually find that the variable in question, like this GDP in the second equation, must Granger cause PCE in the second equation. So let's do that. GDP in the second equation's coefficient is C8. So to test for Granger causality, we are saying so we are saying C8 is equal to 0. C8 is equal to 0. I've typed it wrongly. C8 is equal to 0. We just test that. It's formality. So we are saying GDP in the second equation, Granger causes PCE at 5% level of significance, right? At 5% level of significance. This is what this result is telling us. In the first one we did, PCE was Granger causing GDP at 1% level of significance. So that's it. So to go to our equations, we go to spec again, and then you estimate that to get to the results. Then we go to the last equation where we are testing GDP Granger causing PDI, C15. Then for PCE, it's C17 and C18 equal to 0. So let's start with the GDP Granger causing PDI, which is C15. You go to C15.
Prof,
Yes.
Prof,
Yes. Yes.
before you proceed,
Yes.
maybe you explain what I asked previously and I got lost or I did not catch it. But let's say in our first equation,
Yes.
you have things on top of the first equation. Okay, in our first equation where they C3 and C3, yeah, C3 and C7.
C7 is the constant.
Now in this is the constant.
C7 is the constant.
Okay,
C14 is a constant.
Okay, so if I'm to elaborate on this equation, it's like me saying PCE Granger's GDP.
Yeah, see, we are testing whether PCE Granger causes GDP. And we found that PCE Granger causes GDP at 1% level of significance.
Okay, and then okay, that one is it's quite easy since there's two variables. Now
Yeah.
in the second one, which are now in the first leg,
This one.
will only maybe perhaps, yeah, that one. So
We
there
are
we are saying
interested
GDP.
here we are interested in GDP Granger causing PCE and not
Okay.
PCE Granger causing itself. So that's why we tested
Oh,
C8 only.
okay, because I was a bit confused. Oh, okay, okay. So you tested C8.
Only, yes, because we are not interested in PCE Granger causing itself.
Okay, and in the first equation, if we are interested in PCE, we test C3.
Yes, we test C3. Then in the last equation, we are saying GDP, we are testing whether GDP Granger causes PCE, and then we are also testing whether PCE Granger causes PDI.
Okay.
So here we do two tests. First is C15 for GDP Granger causing PDI. Let's do that. So is that coefficients, diagnostics, world coefficients? Then you say C15 is equal to 0, right? And as you can see, our results are telling us that GDP is Granger causing PDI at 5, is it at 1% level of significance? At 1% level of significance, right? Then we can repeat the test. To go back to the equations, you click on the specification. To estimate, you go back to estimate. Now, the last one that we want to do is whether PCE Granger causes PDI. And we are going to use C17 and C18. C17 and C18 is our now hypothesis. So you go to coefficients, diagnostics, world coefficients, diagnostics. Then you go to C17. C17 is equal to C18. C18 is equal to 0. Right. You test that, and this is what you get. So this is telling us that PCE Granger causes PDI at 1% level of significance. Right. So this is how you do your Granger causality test. And in what we have done, we have assumed that the variables are integrated of order 0 because we are using them in levels. I'm sure you have seen that the variables are integrated of order 0, right? That's why we have actually used them in the levels without transforming them to first differences. I hope you are following that. So that's how you do. In fact, there's something new that you have learned. You have learned how you create a parsimonious equation. Did you understand that part?
Yes, sir.
Yes. Okay, great. If you understood that part, then you can always apply it when you are doing your own work. You can always apply that technique when you are doing your own things. All right. So the next thing, what should I do now? Let me name this. I've named it System 1. And I will close that. Now, the next thing that I want us to do, I want us to use I want us to estimate a var by using this lag length, which was determined by eViews as the optimal lag length. eViews suggested that 1 is the optimal lag length. So I go to estimate once again. Where we have the lag, I change the lag to 1. I change the lag to 1. So if you change the second number from 2 to 1, you are changing the lag for each of the variables to 1. That is what it means. So this is what I've done. Now we estimate the equation, and this is what we get. These are all our results. If you look, the included observations are 33, and the number of parameters is now fallen to 12. I'm sure you can see that, which means you can estimate this equation because the number of coefficients, number of parameters is smaller than the observations included after adjustments. Okay, so this is a feasible estimation. Now, if you look, you can see this coefficient is insignificant. This one is significant. It's close to 2. This one is significant. This one is significant. This one is significant. This one is significant. This one is not significant, not significant, significant. This one is significant, not significant, significant. So as you can see, the majority of the parameters are now significant. So to see this, let's repeat what we did last time. We are going to go to proc and make system and order by variable. Make system and order by variable. These are our equations. The first equation, the second equation, and the third equation. And the last number, the last coefficient there, C4 is the constant in the first equation, C8 constant in the second equation, C12 constant in the third equation. Right, so this is it. Then we can, if we estimate this, we will be able to see the probabilities. So let's estimate this now to see the probabilities. These are our probabilities. And I'm sure if we remove those that are not significant, which is this one and this one, we will have a model similar to the one that we estimated earlier, right? Let's see. Let's see what I'm saying. So we need to test whether C3 and C7 are redundant, right? Let's test whether C3 and C7 are redundant. So we can use the world test to do that. The world test, C3 and C7. We are testing whether they are not significant in explaining the dependent variables. So C3 is equal to C7 is equal to 0. So if the probability is what? Is not less than 5%, then these variables are truly redundant. So these variables are redundant. They are not significant in explaining the dependent variable. They are not significant. So they are redundant, which means we can drop them from the equations. So C6 and C7. C6 and C7. Then we go to specification. We want to remove C6 and C7. Where is C6? It's here. We remove C6. We remove C6. Then we remove C7, which is that. Which is that. Right. And then it do estimate again. Let's estimate again. I think there are 2 pluses there. Let me remove 1. We estimate again and see how our results change. As you can see, we still have a problem somewhere. This one is insignificant. C1 is insignificant as well. So let's test if we should drop these 2 again. C1 and C3. C1 and C3. So we do the redundancy test using the world test again. C1 and C3. C1. We are removing C1. 1. And the C3 is equal to 0. C1 and C3 is equal to 0. Yes, they are redundant. They need to be removed. They are redundant. They need to be removed. They need to be removed. So we go to, what have I done? Let me go back to the system. Okay. So we go to specification. So we remove C1 and C3. We remove C1 and C3. We remove C1 and C3. That's it. Then we estimate again to see how our results change. C1, C3 removed. Right. We now have, yeah, almost perfect. I think this last one, we can leave it because it's a constant. This C12, we can just leave it as it is. Then you can test for your Granger causality by using these results, which obviously gives you the fact that each of those variables, in fact, if I can just scroll down, here PCE, you remember this equation. This is the equation that we had after eliminating that model with the two lags. This is the first equation that we had. Then
Yes,
if you go to the next one, we have this one. There was another variable that was explaining this, but we tested GDP, Granger causing PCE, which was significant, of course. Then for the last one, we had the two PCEs. Now we have one PCE. It's because of the difference in the specification that we've done, but we have GDP, Granger causing PDI, and PCE, Granger causing PDI. So basically, whether you use the optimal lag of 1 to do your estimation or the lag of 2 and then do some eliminations, the results that you end up with are more or less the same. That is the point that I'm trying to emphasize. But the challenge here is that this second equation appears to have autocorrelation. This one does not have autocorrelation. This one may not have autocorrelation, but the second one is autocorrelation because the DW is too small. Autocorrelation because there is a PCE that was here in the previous model that we estimated. Because we had PCE1 and PCE2, both explaining PDI. I'm sure that is what is causing that autocorrelation. So maybe if we add that second lag of PCE, then it would actually help to resolve the autocorrelation problem that we are seeing there. Okay? So this is how you do it. This is how you do it. Next.
Sir,
Yes.
is it not time to stop the recording and restart again?
Okay, let's stop at the 7 exactly. Thanks for reminding me. All right. So that's it. Now, there's something that I need to do before we go on. There are some tests that we need to do. Name this. Okay. This. Right. So we have system 1, system 2. I want to go back to, no, not this one. Let me go back to the system that system 1, this one. Right. This is the first model we estimated. So I want to estimate this once again. So this system 1, correct. Now, I want us to do certain tests, diagnostic tests for this model. The first diagnostic test is the residuals. I cannot do the other test because there are some limitations here, but I can do the normality test. I can do it. And the normality test is telling us that there is no normality problem in equation 1 and equation 2, but there is a normality problem in equation 3 because the probability is less than 5%. The other two have probabilities that are greater than 5%. So we have a normality problem in one of the equations, the last equation, not the first two equations. So that's one diagnostic test that you can do. Then you can also do the correlogram test for autocorrelation. Let's see the way it's appearing. I didn't teach you this. So let me let me see the other one. Yes. Yes, this is an autocorrelation test. And the null hypothesis, no residual autocorrelation up to H lag, right? No residual autocorrelation up to H lag, and the number of lags given are 12 here. And all the probabilities are greater than 5%. This is another test for autocorrelation that you can use. So all the probability values are greater than 5%, which means there is no autocorrelation in this model. That is what this means. So you look at the probability values, if they are greater than 5%, there is no autocorrelation. At the lags selected by eViews, because we didn't select this, it's eViews that selected those lags. So there is no autocorrelation. Even here, there is no autocorrelation. Using the Q-stat, there is no autocorrelation. Even the adjusted Q statistic, there is also no autocorrelation. So it's actually two tests in one, the Q statistic and the adjusted Q statistic, right? And their probability values are all greater than 5%. So there is no autocorrelation, which is good. Then you cannot test for heteroscedasticity here. That's it. I think for now, we just leave it as it is. So I'm going to stop this recording now. Let me stop this recording and maybe we can have a 1 minute break. Stop recording. Okay.